And ninth one, a DC electrical motor is used to operate a hoist mechanism in a crane. Okay, a motor. So there's a hoist mechanism in a crane. Okay, something like this. And this motor is supplied with, say, a battery. Okay, and it supplies 150 volts, 10 ampere DC for a period of 2 minutes. So that is the energy supplied to the motor. So the motor rotates, and the torque provided by the motor to hoist shaft, this is the hoist shaft, that is torque provided is 230 Newton meter, and this rotates at an RPM of 60. The hoist mechanism, this is hoist mechanism, lifts, so 3-ton mass is lifted through a height of 5 meters. So this is what is happening. So now calculate the work interaction for the DC source. This is battery. DC source is a battery, motor, hoist and mass, this mass. So for this we have to consider systems. System as battery. Okay, like this. What happens? Some energy goes out of this, electrical energy goes out. So hypothetically, if I connect a motor, pulley, etc., what is the work involved for the DC source will be equal to 150 volts into 10 amperes into 2 minutes. So 2 into 60. That will be the, that is 180,000 joules. That will be the work. So that is the basic energy source for us. So this does the positive work. Now for the motor, W for the motor, if you take as the system, it receives some energy from the DC source and delivers some energy to the shaft, hoist shaft. Okay, so that means it is minus work DC plus the work it does is the rotating of the shaft, which is nothing but 230 into 2 pi 60 into 2 minutes. This is RPM, rotations per minute. Okay, that is angle, this is RPM is 60. So 2 pi into 60 is angle, total theta, and this is T in Newton meter. So T into theta. So how much total angle rotated is 2 pi 60 into, it is turning for 2 minutes. So this will be the total theta for me. So when I do this, I get minus 180,000 plus 173,415.9, which is equal to minus 6,584.1 joules. So you can see that there is it takes more energy from the DC source. Motor takes more energy from the DC source, but due to some efficiency, it is delivering something lesser. Out of 180,000, it is delivering about 173,000. So that is a negative network for this. Okay, now let us say what is hoist. Hoist is equal to minus W, because it takes motor's work, plus it lifts the weight. So that is what, 3 tons, 3 into 1000 kgs into G, 9.81, this is M and this is G, into height, H is 5, this is H. So that is the thing is then that will be equal to minus 26265.9 joules. So and finally I get work for the mass is equal to minus mgh. It doesn't do any other work, so it just is being carried up by the hoist. So that will be minus 147,150 joules. So now we can see that after calculating the work for individual components by taking the system as the particular component itself, I can now prove that work DC plus work motor plus work hoist plus work mass will be equal to 0. So this will be the sigma W, which is equal to 0 for me. So this demonstrates that, so that this is problem which covers all other form of work. It covers electrical work, it covers shaft work, it covers the work done against the gravity. Okay. So this is the problem number 9. Okay, now this problem, a spherical balloon of diameter d1. Okay. So a spherical balloon of diameter d1 is the diameter when the pressure is P1. So the pressure of the gas inside the balloon is P1. Atmospheric pressure is P0. Pressure of atmosphere. A process now occurs. What will be the process? The diameter increases to D2. D2 and pressure is proportional to the diameter of the balloon. So derive expressions for the work interactions for the gas and for the atmosphere. So here first of all, pressure of the gas is proportional to the balloon diameter. So I can say P equal to A plus B times the diameter of the balloon. Now when no gas is in the balloon, what happens? Pressure equal to 0, T equal to 0, correct? So that means A will be equal to 0. Sorry, pressure is not 0, pressure will be atmospheric pressure P naught. So A will be equal to P naught. Okay, because a flat balloon, atmospheric pressure will act on this. So when diameter is 0, pressure is P naught, so A equal to P naught. Then I can substitute this P equal to P1, D equal to D1, which implies P1 equal to P naught for A into B into D1, which implies B equal to P1 minus P naught by D1. That is the relation I get. Now work interaction for the gas will be equal to integral 1 to 2 P dV is equal to D1 to D2. It is going to D1 to D2. I will say P naught P naught plus P, that is A plus B I am saying, by D1, it is A plus B into D into dV. This is P, correct? Into dV. Now, what is V? V is equal to 4 by 3 pi r square for the, pi r cube for the balloon volume of the balloon. So, in terms of diameter, this is pi d cube by 6. That means dV can be written as pi d square by 2 into d diameter from the definition of volume. So, I substitute this here. Then I will get W gas is equal to integral d1 to d2 P naught plus P1 minus P naught by d1 into d into pi d square by 2 into dd. So, when I integrate this, finally I will get P naught pi d2 cube minus d1 cube by 6 plus P1 minus P naught by d1 into pi into d2 power 4 minus d1 power 4 divided by 8. So, this is the expression, that is what we want. Okay. Next problem is on heat transfer. 600 kg of food product initially at 5 degrees in a refrigerator, say, has to be frozen now for keeping it for long period and stored at minus 15 degrees centigrade. The freezing point of the food product is minus 5 degrees centigrade, freezing point. Then the latent heat of fusion or latent heat of freezing is given as 235 kilojoule per kg. The specific heat of the product above the freezing point is C, 3.18 kilojoule per kg Kelvin, and the specific heat below the freezing point is 1.72. So, what happens? First, I have to remove heat. So, from 5 degrees centigrade, I have to first cool it to minus 5 degrees centigrade, freezing point. Okay, cool. So, I will say cooling cycle 1, in which I cool sensibly when temperature is above the freezing point. So, 5 degrees centigrade to minus 5 degrees centigrade, which is the freezing point, is attained. Now, this is sensible. So, I have to use 3.18 C equal to, say 3 C1 equal to C 3.18 kilojoule per kg Kelvin, that is 1. Then the second cycle is cooling cycle 2, I have to freeze it, freezing by supplying latent heat, removing latent heat of fusion. This occurs at constant temperature. Of minus 5 degrees centigrade. So, here it is basically minus 235 kilojoule per kg. I have to remove this heat, I have to remove. Then cooling 3 is minus from minus 5 degrees centigrade, where it has now frozen, to decrease the temperature to this. Here I have to use C2 as below the freezing point, 1.72 kilojoule per kg Kelvin, that is it. So, for I will say Q1 is the heat to be removed in the cooling cycle 1, Q2 is the cooling cycle, cooling 2, Q2 is the heat removed, and here Q3. So, Q1 will be equal to mass. So, M is given as 600 kg. So, I will say M C1 into T2 minus T1, that is minus 5 minus 5. So, that will be equal to 600 into 3.18 into minus 10 equal to minus 19080 kilojoule, that has to be removed. Then Q2 will be equal to minus 600 into 235. So, kilojoules per kg into this kilojoules, that is minus 141000 kilojoules, and Q3 will be equal to MC2 into final temperature is minus 15, initial temperature is minus 5. So, that is this, that will be equal to 600 into, now you have to use 1.72 into minus 15 minus 5, which is equal to minus 320 kilojoules. So, the total heat to be removed to achieve cooling of product from 5 degrees to minus 15 degrees will be equal to 170,400 kilojoules. This is the heat which has to be removed. So, this is last problem again on heat transfer. Here it is desired to melt aluminum from a temperature of initial temperature of 15 degrees centigrade. Now, this is first of all solid at 15 degrees centigrade. Now, first of all it has to be heated to some temperature called melting point, that is 660 degrees centigrade. So, sensibly aluminum solid has to be heated from 15 degrees to the melting point, where the specific heat of solid state is given as 0.9. That has to be used to calculate the heat required to heat that, sensibly heat that. Then the latent heat is given as 390 kg per kilojoules. So, that has to be supplied to melt it at the constant temperature of the melting point. So, now molten aluminum at 660 degrees is available. Okay. So, density of the molten aluminum is given here, and finally the temperature has to increase from 660 to final temperature of 700 degrees centigrade. Okay. Now, this has to be done in a furnace. Okay. This has to be done in a furnace which has a power rating, thermal power rating, this is called thermal power rating of 217 megawatts, but its efficiency is 70%. That is, out of the 270 megawatts which is heat generated in the furnace, 70% can be transferred to the aluminum. So, please understand, any phase change problem, in the previous problem it was cooling. Say for example, a liquid food at 5 degrees is cold, first it is frozen to minus 5 degrees, which is the freezing point, then it is further cooled to below its freezing point to minus 16 degrees, that is a cooling problem. Here it is heating, initially starting as a solid from 15 degrees, its temperature is raised to 660 degrees where it will melt. Then for melting I have to supply the latent heat of melting here, 390 which is given. Then the molten aluminum, the liquid state aluminum has a different Cp value that should be used to increase the temperature from 600 to 700. So, what is the per kg, let us say per kg aluminum, what is the heat required to rise temperature from 15 degrees centigrade to 660 degrees centigrade, which is melting point, that is Q1 is equal to what, 0.9, which is a solid state Cp C value into delta T, 660 minus 15. So, that will be equal to okay, that is some value, the intermediate value is I do not know that. Then similarly Q2 will be equal to latent heat at the melting point, I have to give the latent heat, that is 390. So, this is also kilojoules because it is kilojoules per kg Kelvin. Okay. So, this will be kilojoule per kg. Similarly, now kilojoule per kg is supplied to melt 1 kg of aluminum, that is the Q2. Then Q3 is raising the temperature from 660 melting point, because here at constant temperature of 660 degrees Celsius, when there is a phase change, solid to liquid conversion, temperature remains constant. Of course, here the pressure also remains constant. So, Q3 is the liquid state specific heat is 1.11 into delta T. What is that? 700 660. So, this is also kilojoule per kg. So, now what is the total heat required per kg of aluminum to melt it and increase the temperature to 700 degrees centigrade, starting from initial temperature of 15 degrees. That will be equal to Q1 plus Q2 plus Q3, which is equal to 1014.9 kilojoule per kg. This is the heat required 1 kg of aluminum to be melted from initial temperature 15 degrees, and the molten aluminum temperature increased to 700 degrees centigrade. So, what is the power available? Power available in the furnace equal to 217 megawatts, that is 217 into 10 power 3 kilowatts, out of which 70% is the efficiency. That means into 0.7. So, that means 217 into 10 power 3 into 0.7 kilojoule per second. That will be the power. Now, what is the mass of aluminum that can undergo this process? That will be equal to, so let us say this is power is say P. So, P divided by Q, that is kilojoules per second, kilojoule per kg. So, this will be kg per second. From this you can calculate. Okay. So, this comes approximately to 530 tons per hour. Okay, not in seconds, I am now converting to per. So, approximately 530 tons per hour is the value. So, in this case you can see that any heat transfer problem, we are trying to calculate the heat required. There are two types of heat supply. First one is sensible heat. If the component is in a same phase, like liquid phase or solid phase, I add the heat, even gas phase, I add what is called sensible heat. So, a particular material will have a specific heat, which is the heat required to rise the temperature per kg of the material to 1 Kelvin by 1 Kelvin. So, for gases we have two specific heats, specific heat at constant pressure, specific heat at constant volume. But for solid and liquids we have only one specific heat, which is called C. So, that is the heat required to rise the temperature of the material 1 kg of the material by 1 Kelvin. Now, this is called sensible heating. Now, when there is a phase change, for example, liquid to solid or solid to liquid or liquid to vapor or vapor to liquid, okay, any phase change, we have to supply or remove what is called latent heat. That will be specified as some kilojoules per kg. Okay, so these are the two things: sensible heating or sensible cooling, then latent heat supply or latent heat removal. These are the concepts which you have to use to find the total heat transfer required. Okay, so these are all the problems, tutorial problems for work and heat transfer. Thank you. I will stop here.